This is the third and last module of chapter 6. In this module, we shall describe two methods to find all eigenvalues and eigenvectors of a real symmetric matrix. The first method is known as Jacobi's method and second method is known as Householder method. In Jacobi's method, a series of orthogonal transformation or rotation is applied on appropriate matrices to convert the original matrix A to a diagonal matrix. The diagonal elements of the diagonal matrix are the eigenvalues of the given matrix A, and from the orthogonal transformation we can calculate all eigenvectors of the original matrix A. The Jacobi's method is applicable for a real symmetric matrix. Here we assume that A is a real symmetric matrix, and from linear algebra we know that there exists a real orthogonal matrix R provided all the eigenvalues are real. Then R inverse AR is a diagonal matrix D. Again, the diagonal matrix D and the matrix A are similar, and hence diagonal elements of the matrix D are the eigenvalues of the matrix A, and the column vectors of R are the eigenvectors of the matrix A. So, this is the main principle of the Jacobi's method. So, the main principle of Jacobi's method is to find the matrix R such that R inverse AR becomes a diagonal matrix. For this purpose, a series of orthogonal transformations or rotations R1, R2 and so on are constructed or applied to the appropriate matrices. Suppose Aij with the largest magnitude element among the off diagonal elements of the matrix A of order n by n. Off diagonal elements means the element other than the diagonal elements. Let the first orthogonal matrix R1 equal to Rij, small rij denotes the ijth element of the matrix R1, be defined as Rij equal to minus sin theta, Rji equal to plus sin theta, Rii equal to cos theta, Rjj equal to cos theta, and all other diagonal elements are unity and all other off diagonal elements are zeros. So, this is the formula to construct the first rotational matrix R1. In explicit form, the matrix R1 is given by equation 2. Note that the ith element of the matrix R1 is cos theta, the diagonal element Ajj is the another cos theta, and off diagonal elements are ijth position is minus sin theta and jth position is sin theta, and the all other diagonal elements are 1 and all other off diagonal elements are 0. It may be noted that the four element cos theta, minus sin theta and cos theta are present in the positions ii, ij, ji and jj respectively in the matrix R1. Let A1 be a submatrix of the given matrix A formed by the elements Aii, Aij, Agi and Ajj. That is, the submatrix A1 of A is a matrix of order 2 by 2 shown in equation 3. Again, let R1 bar be a submatrix of the matrix R1 defined by R1 bar equal to cos theta minus sin theta, second row is sin theta cos theta, where theta is an unknown quantity known as rotational angle. That means R1 bar is a submatrix, and obviously this matrix is an orthogonal matrix, and hence the original matrix R1 is also an orthogonal matrix. The matrix R1 bar is orthogonal, obviously it can be proved by direct multiplication. Now we apply the orthogonal transformation R1 bar to A1 such that the matrix R1 bar inverse A1 R1 bar becomes diagonal. Now R1 bar inverse into A1 into R1 bar, which is equal to, this one is the R1 bar inverse, this is A1, this one R1 bar. After multiplication it becomes a 2 by 2 matrix whose elements are shown in last matrix. Note that this is a symmetric matrix. The off diagonal elements are same. The off diagonal element is ajj minus aii whole into sin theta cos theta plus aij into cos 2 theta, and the diagonal elements are different. Our intention is to find the value of theta in such a way such that R1 bar inverse into A1 into R1 bar becomes a diagonal matrix. Therefore, we choose the off diagonal element of R1 bar inverse into A1 into R1 bars as 0. Therefore, ajj minus aii whole into sin theta into cos theta plus aij into cos 2 theta equal to 0. Or from this equation we get tan 2 theta equal to 2aij by aii minus ajj, or this equation can also be written as theta equal to half of tan inverse into 2aij by aii minus ajj. That means equation 5 or equation 6 gives the values of theta, that means gives the rotational angle theta. This equation gives 4 values of theta, but to get the smallest rotation, theta must satisfy the inequality, that means the theta should lies between minus pi by 4 to plus pi by 4. From equation 6, we can conclude that if aii not equal to ajj, then the equation 6 is valid for any arbitrary aii or aij or any other elements of the matrix A. But if aii equal to ajj, then theta equal to plus pi by 4 if aij greater than 0, and theta equal to minus pi by 4 if aij is less than 0, that means if aij is negative quantity. That means equation 6 and 7 are used to determine the angle theta. So, for this rotation, the off diagonal elements of the matrix R1 bar inverse into A1 into R1 bar vanish and the diagonal elements are updated. Let R1 inverse AR1 be the diagonal element D1, that means D1 is taken as R1 inverse AR1. If D1 is a diagonal element, that means if D1 is a completely diagonal element or diagonal matrix, then no further rotation or transformation is required. But if D1 is not a diagonal matrix, then next iteration is required. If D1 is a diagonal matrix, then the diagonal elements of the matrix D1 are the eigenvalues and the column vectors of R1 are the eigenvectors of the matrix A. Otherwise, another rotation or iteration is required to reduce or to get the diagonal element or diagonal matrix corresponding to the matrix A. In next iteration, the largest off diagonal element in terms of magnitude is determined from the matrix D1, and the same method is applied to find another orthogonal matrix R2 to compute the matrix D2. That is D2 equal to R2 inverse D1 into R2, where R2 is the next orthogonal transformation matrix, D1 is the first iterated matrix and D2 is the new iterated matrix. By substituting the values of D1, we get R2 inverse into R1 inverse AR1 into R2, that means R1 inverse AR1 is nothing but the value of D1, and this expression can be written as R1 into R2 whole inverse into A into R1 R2. In this process, a series of orthogonal rotations are generated. At the kth iteration, the matrix dk is given by dk equal to rk inverse, rk minus 1 inverse dot 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 r1 inverse A r1 r2 dot 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 rk minus 1 into rk. This expression can be written as r1 into r2 dot 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 rk whole inverse into A into r1 r2 dot 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 rk, and let this expression be R inverse AR, where the matrix R equal to the product of the orthogonal transformation R1 into R2 dot 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 RK. Now, if dk is a diagonal matrix, Then the diagonal elements gives the eigenvalues of the given matrix A, and the column vectors of the matrix R gives the corresponding eigenvectors. According to the principle of Jacobi's method, when k is a large number or k tends to infinity, the matrix dk becomes a diagonal matrix. The diagonal elements of dk are the eigenvalues of the matrix A, and the columns of R are the corresponding eigenvector. Thus, Jacobi's method determines all eigenvalues and eigenvectors of a real symmetric matrix. But the method has a drawback. The elements which are transferred to 0 at any particular iteration, that element may not remain 0 during next iteration. This is one of the major drawback of this method. The number of upper diagonal elements of a symmetric matrix of order n by n is n into n minus 1 by 2. It is obvious the number of half off diagonal elements is n into n minus 1 by 2. Therefore, to make all off diagonal elements to 0, it is expected that n into n minus 1 by 2 rotations are required to convert the original matrix to a diagonal one. But for some problems, we see that the number of such rotations may be less than this number, and also for other some problems we have seen that this number is more than n into n minus 1 by 2, that means the more than expected number of rotations. Now, we consider an example to illustrate the Jacobi's method to find all eigenvalues and eigenvector of a real symmetric matrix. So, this is a real symmetric matrix of order 3 by 3. The largest off diagonal element is 3, which is present at positions 1, 2 and 2, 1. Therefore, the first rotational angle theta is given by the formula tan 2 theta equal to 2 into a12 by a11 minus a22. Here we have assumed that the largest element 3 present at position 1, 2. So, for this reason the formula is taken as 2 into a12 by a11 minus a, which is equal to 6 by 0, that means infinity, and hence theta is equal to pi by 4, because a12 is positive quantity, therefore theta is positive pi by 4. Thus, the first orthogonal transformation matrix R1 is given by equation 9. R1 equal to, the first row is cos pi by 4 minus sin pi by 4, 0. Second row is sin pi by 4, cos pi by 4, 0. Third row is 0, 0, 1. And in terms of ordinary real number, it becomes 1 by root 2 minus 1 by root 2, 0, 1 by root 2, 1 by root 2, 0, 0, 0, 1. So, R1 is given by equation number 9. Therefore, the first rotation yields the matrix D1 equal to R1 inverse A R1. After simplification, this becomes the matrix whose first row is 5, 0, 1.41, 4, 2, 1. Second row is 0, minus 1, 0. Third row is 1.41, 4, 2, 1, 0, 3. It may be noted that this is not a diagonal matrix. So, next iteration is required to convert D1 to a diagonal matrix. The largest off diagonal element of the matrix D1 is now 1.41421, and it is present at position 1, 3, and the second rotational angle theta is given by theta equal to half into tan inverse 2 into a13 whole divided by a11 minus a13, and it is equal to 0.477658. So, using this theta, the second orthogonal matrix R2 is given by a 3 by 3 matrix whose first row is cos theta 0 minus sin theta, second row is 0, 1, 0, third row is sin theta 0 cos theta. So, after simplification, the matrix R2 is given by equation 10. Then the second rotation gives the second matrix D2 equal to R2 inverse D1 R2, which is equal to a diagonal matrix. Note that in this case D2 becomes a diagonal matrix. So, no further rotation or transformation is required for the matrix D2. So, diagonal elements of this matrix D2 are the eigenvalues of the matrix A, the given matrix A. So, here we have concluded that D2 becomes a diagonal matrix, and hence that eigenvalues of the matrix A are 5.73205, -1 and 2.26795. These are the eigenvalue of the given matrix, and the eigenvectors are the columns of the matrix R, where the matrix R is the product of R1 and R2. And after simplification, this matrix is given by equation number 11. So, from this matrix we can determine the eigenvectors corresponding to the above eigenvalues. Hence, the eigenvalues are 5.73205, -1 and 2.26795, and the corresponding eigenvectors are the column vectors. First one is 0.62796, 0.62796, 0.45970. This is coming from the first column of the matrix R, and second eigenvector is the second column of the matrix R, and third eigenvector is the third column of the matrix R. So, these are the eigenvalues and eigenvector of the given matrix M. So, the Jacobi's method is described to find all eigenvalues and eigenvector of a real symmetric matrix. This method is one of the good methods to find all eigenvalues and eigenvector of a real symmetric matrix. But the number of rotations of this method depends on the given matrix, because if an off-diagonal element becomes 0 in a particular rotation, then there is no guarantee that that particular element remains 0 in successive iterations or rotations. So, due to this drawback, the number of iteration cannot be specified for this method, but this drawback is removed in next method called householder method. Now, we consider a real symmetric tridiagonal matrix. This is a particular case of a real symmetric matrix. Let A be a real symmetric tridiagonal matrix, where the matrix is defined as the diagonal elements of this matrix are A1, A2, A3 up to An, and upper diagonal elements are B2, B3 up to Bn. And since the matrix is symmetry, therefore, the lower triangular elements of the matrix A are B2, B3 up to Bn. So, for this matrix, the characteristic equation is denoted by Cn lambda, where lambda is the variable and n represents the degree of the characteristic polynomial or equation, and it is defined as this equation or this matrix. The recurrence relation for Cn lambda is given by Ck plus 1 lambda equal to A k plus 1 minus lambda whole into Ck lambda minus B k plus 1 whole square into Ck minus 1 lambda, where C0 lambda equal to 1 and C1 lambda equal to A1 minus lambda, and this is true for all k equal to 1, 2 up to n minus 1. So, from this relation, from this recurrence relation given in equation 12, we can construct the complete characteristic equation for the given symmetric tridiagonal matrix. If all the elements B2, B3 up to Bn are non-zero, then Cn lambda becomes a Sturm sequence. By Sturm theorem, we can find an interval which contains an eigenvalue or the root of the characteristic equation of the matrix A by substituting different values of lambda in equation 12. Let n lambda be the number of changes in sign in Sturm sequence for different values of lambda. Then difference of Na minus Nb, difference of Na and Nb, that means the absolute value of Na minus Nb, represents the number of eigenvalues or number of roots lie within the interval AB, where Cna and Cnb are non-zero. That means the characteristic equation or the characteristic polynomial Cna and Cnb are non-zero. If the location of an eigenvalue is known, then using any method such as Newton-Raphson method, fixed point iteration method or bisection method, etc., one can find an eigenvalue. Repeating this method, we can find all eigenvalues of a real symmetric tridiagonal matrix A. After computing of eigenvalues, one can calculate the eigenvectors directly from the equation A minus lambda I into x equal to 0. This is the fundamental expression to find the eigenvectors of any matrix A. Now we explain the householder method to find the eigenvalues of a real symmetric matrix. But the main principle of this method is to convert the given real symmetric matrix to a real symmetric tridiagonal matrix by applying a series of orthogonal transformation like Jacobi's transformation or rotations. Then using the method described in previous section, one can find all eigenvalues and corresponding eigenvectors of a real symmetric matrix. In each iteration, a complete row of zeros in appropriate position is produced without changing rows obtained in the previous rotation. Thus, n-2 householder transformation are required to get the tridiagonal matrix. That means, in householder method, the number of rotation is determined from the order of the matrix. It does not depend on the elements of the matrix. But in Jacobi's method, the number of transformation or rotation depends on the elements of the matrix A, not the size of the matrix. Now, the following orthogonal transformation is used in householder method. The transformation formula is given by 13. That one is R equal to 1 minus 2 into S transpose, where S is a vector given by this relation, that means S equal to small s1 comma small s2 up to small s1 transpose. That means S is a column vector or column matrix containing n components, and the element of the vector S must satisfy the condition given in equation 14. That means STS equal to 1, that means sum of the square of the elements of S is 1. Now we construct a sequence of rotations defined below. AI equal to Ri into Ai minus 1 into Ri, where I equal to 2, 3 up to n minus 1. So this is the sequence of rotations given or applied on the given matrix A, where the rotational matrix Ri equal to I minus 2 into Si transpose, where Si, that means ith orthogonal transformation vector, is equal to 0, 0 up to 0. That means the first I minus 1 elements are 0, and the next elements, that means Si plus 1 to Sn, are not necessarily equal to 0, and the elements of this vector Si satisfy the condition Si square plus Si plus 1 square plus dot 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 plus Sn square equal to 1. That means sum of the square of the element of Si equal to 1, and initially A1, the first transformation matrix or rotation matrix A1 equal to A, the given matrix A. In first transformation, we determine SIs, that means the elements of the vector Si, capital Si, in such a way that the elements in the previous position, in this position 1, 3, 1, 4 up to 1n of the matrix A2 becomes 0. Also, the elements in the corresponding position in first column become 0. That means first column and second column are same, because the transformation is symmetry and the given matrix is also symmetric. Therefore, the first transformation produces n minus 2 zeros in the first rows and first column. In second transformation, the element in position 2, 4, 2, 5 up to 2n and 4, 2, 4, 5, 2 up to n2 are transformed to 0. That means the elements of the second column and element of the second rows are transferred to zeros. Thus, n minus 2 householder rotation is needed to obtain the tridiagonal matrix A n minus 1. That means we have generated a sequence of matrices, tridiagonal matrices A1, A2 up to A n minus 1. Now, the Householder method is explained by considering this matrix. The problem is reduce the matrix A of order 4 by 4 into the tridiagonal form using Householder method. In first rotation, the rotational vector S2 is taken as 0, the first element is 0, other elements are S2, S3, S4, this is a column vector, and the element, intermediate element Q is defined by the sum of square of the elements of first row except the first element, and this is equal to root 6. The second element of the vector S2, capital S2, which is equal to S2 square equal to 0.7041, and finally S2 equal to 0.8391. Similarly, S3 equal to 0.4865, S4 equal to minus 0.2433. So, these are the elements of the vector S2. That means S2 is equal to a column vector whose first element is 0, second one is 0.8391, third one is 0.4865, and last element is 0.2433. Thus, the second rotational matrix R2 equal to I minus 2 into S2 transpose. So, after using the values of the vector S2, we get the matrix R2 given by equation 17. Now, the rotational matrix A2 is equal to R2 into A1 into R2. After simplification, the matrix A2 is a 4 by 4 matrix whose first element and first columns and last columns are zeros except the first two elements, and this is expected as per the definition or the rules of Householder method. Now, we apply the second rotation. In second rotation, the rotational vector S3 equal to 0, 0, S3, S4, this is a column vector, and Q equal to 0.5774, S3 equal to 0.8396, S4 equal to 0.5431. Therefore, the rotational vector S3 equal to 0, 0, 0.8396, 0.5431, correct up to 4 decimal places. Then the rotational matrix R3 is given by equation number 19. Note that the first two rows and first two columns are 0 except the diagonal elements. Then the matrix A3 equal to R3 into A2 into R3. After simplification, this matrix is given by equation number 20. Note that the matrix A3 is a tridiagonal matrix. This is the required real symmetric tridiagonal matrix. Now, from this tridiagonal matrix, we can find all eigenvalues and eigenvector of the given matrix A using the method described in section 2. That means, we have described one method to find all eigenvalues and eigenvector of a real symmetric tridiagonal matrix. So, Householder methods gives all eigenvalues and eigenvector of a given real symmetric matrix. So, in this chapter we have described Leverrier-Faddeev method to construct a characteristic equation of a matrix. From this equation we can find all eigenvalues of a matrix, and also we have described 4 methods to find eigenvalues and eigenvector. Ratishauser method is used to find all eigenvalues of a matrix. The power method determines the largest and least eigenvalues and corresponding eigenvector of a matrix of any arbitrary matrix, and Jacobi's method and also the Householder methods are used to find all eigenvalues and eigenvector of a real symmetric matrix. Also, a suitable method is described to find all eigenvalues of a real symmetric tridiagonal matrix. So, using this method or from this method we see that the computation of eigenvalues and eigenvector is not a simple task, it needs a lot of computation time. Several other methods, other efficient methods are available to find eigenvalues and eigenvector of a matrix. These are available in literature.